All right. Xavier Amatriain?
That's pretty close, yeah.
Pretty close. He's a research engineer and manager at Netflix. Prior to this, he was a senior researcher at Telefonica and also worked as a technical director of the Allosphere project at UC Santa Barbara.
Okay, yeah, so thank you very much. So yes, I'm a research and engineering manager at Netflix, and I'm going to be talking today about one of our most valued assets at Netflix, which is our personalization or recommendation. So saying that I come from a company and I'm going to talk about one of our most valued assets is my subtle way of saying that I'm not going to be giving too many technical details. Of course, I hope that I will make this presentation interesting to you for a different reason, because I'll be talking about the application of machine learning, data streaming processing in the context of customer-facing and industrial-scale applications such as Netflix. So I think there will be plenty of interesting things in the talk for you. Okay, so how many of you are familiar with the Netflix prize? Hands up. Okay, how many of you actually downloaded the data and played around with it, try to win the $1 million? Okay, that's pretty good. So for those of you that are not so familiar, let me remind you, this is a contest we put out at Netflix in 2006. What we were really interested at that time is how can we make better recommendations. But of course we had to find a proxy question, something that was measurable, something that we would put a number on, and that's the accuracy in predicted rating. So whoever was able to improve 10% the existing method would win $1 million. So here are some details on the contest. There were 100 million ratings on 18,000 movies and around 500,000 users. And those ratings were from 1999 to 2005. And the contest, you had to pick 2.8 million ratings, which roughly was around 6 per user. With 10% better RMSE, that was a success metric we chose at that time. Okay, so in 2007, a year later, there was the Progress Prize. The famous Corbell team from AT&T at that time improved by 843, so that was getting close to the 10%, using a linear combination of 107 prediction algorithms. The top two algorithms out of those 107 were SVD, so form of matrix factorization that probably most of you know, which had an RMSE on the prize data set of 0.89, and RBM, restricted Boltzmann machines, which had an RMSE of 0.899, so pretty close. The linear blend had an RMSE of 0.88. So those are two of the 107. So what we did, because we got the source code for that, is we took that source code, we went through some of the limitations, for example, the fact that they were designed for 100 million ratings, and we had roughly around 5 billion, and they were not adaptable to adding ratings to the users, and had some performance issues. So we went through that, we re-implemented the methods, and those are part of Netflix rating prediction today. Now the question we get all the time is like, okay, that was the Progress Prize, what about the final ensemble? Because in 2009, so that was 2 years later, somebody, actually the same team, joined forces with some other teams. They were able to beat the 10%, they won the $1 million, and they added many more algorithms to these 107 they already had. What did you do with that? So the answer to that is we're not using it. We're not using it, and there are several reasons for that. The main one was, again, think about the Progress Prize improvement, 8.5% more or less. This was 10%. It was much more complex. The engineering effort we had to do to scale those algorithms was not worth it. And it was not worth it, not only because of the increase in accuracy, but also because the focus had changed by that time. And the focus on rating prediction was not so important as something else that I will be talking later on through this talk. So just to give you some rough idea, I'm not going to go through the details of how Netflix has changed since that time, but basically here, 2006, we announced the prize. That was before we had streaming. That was before we were available on devices, for example. We gave the prize here in 2009, and then after that, we went to the iPhone. We went to a bunch of other different countries. We launched the Facebook integration across the world last year. So all these things especially the streaming and the devices, change their focus. And now rating prediction is only a very tiny part of what we do in Netflix recommendations. Now, what do we do? I'm going to walk you through the anatomy of Netflix personalization, the kind of data, the kind of algorithms that we use. So for those of you, especially those of you that are not from a country where you have Netflix really available, this is how the website looks, and most of the devices have a similar look, where we have rows and we have ranking. And something very interesting, we're not personalizing for a single user, we're personalizing for a household. And that adds a bunch of requirements, which are such as diversity, which is something that we need to take into account. So this is the top 10. This is one of the rows we use and one of the algorithms we use to personalize and to give you tailored recommendations. Top 10 already points to a few of the things that we do. For example, we use awareness, or we try to make the user aware of the things that we do to personalize, and that actually increases user engagement. We have measured that. We also use diversity, so our algorithm not only tries to maximize a single metric, but it actually tries to play around with the idea of the household and the fact that we're going to have different people looking at this and trying to play from this list. We support recommendations, so again, algorithms are not only meant to give you the results, but also to give some support and some explanation of why we're recommending something. Rating prediction, for example, now it's more useful as a support metric than actually as a prediction metric. We use things like we tell you what we have based this recommendation on. We even use social support whenever we recommend something if you're connected to Facebook. That's outside of the US because it's not available here. Okay, social recommendations, the same. It's not available in the US, but we're starting to tap into getting all this stream of data that we get from Facebook connected friends that are watching and are liking whatever you watch. And the genre roles. This is probably like what most people know and realize when they start using Netflix. They get all these weird genre roles that are specifically tailored for them, right? And you get like inspired biographic comedies from the 80s, and there's like very tailored genres that are made for you. And those have proven actually to give satisfaction. And again, they're not only giving you a recommendation, they're giving context and evidence and support for what's being recommended. We use implicit input based on your recent plays, and we also use explicit based on your taste preferences. That's something, another source of data that we get, users telling us explicitly what kind of genres they use. And diversity, again, and freshness, those are these two other side requirements that we take into account all the time. Similarity is another source of recommendations that use throughout. We use machine learning models that have different features, like, for example, what is similarity, right? You can think of similarity based on metadata or content. You can use similarity based on ratings, rating patterns, viewing data, all of that. And why not? You can throw all that and learn the concept of similarity in the context where you're actually using it. For example, we use it whenever you add something to your queue. When you search for something, we give you similars. And then we can use the feedback from the user to actually learn what the concept of similarity is using machine learning models. And ranking has become sort of like one of our top priorities, much more so than ratings or rating prediction, for example. So think of ranking as scoring, sorting, and filtering in a personalized way. So that's kind of like what search engines do, but we add the personalization factor, which is also available in many search engines. But the goal here is to find the best possible ordering for a user within a specific context and in real time. That's also very important because we need to take into account the user intent. The objective is to maximize consumption, and this is something similar to the CTR click-through rate prediction for ads or search, except that it adds a little tweak, because we're not only interested in you clicking on something, but it's actually clicking and watching and then coming back and watching again. So that adds some extra requirements on our objective function. And you can think about it, if we get you to click many times, but you don't end up watching whatever you clicked on, that's a very bad sign, right? So we don't want to fool you into clicking things that you don't end up liking. We take into account, again, factors like accuracy, novelty, diversity, freshness, and so on. So the obvious baseline for ranking is popularity. If I knew nothing and I had to guess for each one of you in the room what you were going to like, I would just go to my list, look at the most popular stuff on Netflix, and give you, each one of you, exactly the same list. Because chances are that the most popular stuff is what most people are going to click on or going to watch. What happens when you add ratings? Well, when you add ratings as an input to ranking, you are personalizing, but you're also increasing your accuracy of your ranking. Yes?
So what is improvement over baseline? What is that number actually?
What does that mean? So we use,
the metric?
yeah, we use many offline metrics, but since we're talking about ranking, think of this metric as a typical metric that you would use in ranking, which is MRR, near reciprocal rank, NDCG, something like that, fraction of concordant pairs. Roughly, they're all the same, right? But any of these metrics are going to give you roughly the same. So we add ratings, and then we increase around 25, 30%. And of course, we add many other features. Now, all these other features that come from the data that I'll be showing you afterwards are just data that we can add to our real-time machine learned models to increase the accuracy. And this is an increase 200% versus the popularity baseline. And when we do a little of parameter tuning, we go a little bit over 220%. Okay, so that leads me to data and models. And I'm going to go quickly through a bunch of different data that we use to do this ranking and to do this personalization. So ratings, we have 5 billion ratings, 4 million ratings a day. We have popularities. The concept of popularity, forget about the global popularity I was talking about. We can make up as many as we want. We can have cluster popularities for different clusters of users. We can have daily, we can have weekly, we can have regional. We can base our popularity computations on as many concepts as we want and use that as real-time data streams that go into our models. The plays, we get 30 million plays a day with start, stop, pause, continue. All that information can be fed into our machine learned models. Item metadata, this is the content side. So we get all this information about every single item in our catalog. Presentation, it's not only about what people actually play, it's what people actually scroll through, whether they stay in a particular view for more seconds or less, whether they click back on their browser, or they just go over and hover over some movie to see the details. All of that information can be used as feedback to the algorithms. Social feedback, I already mentioned, and many others. All of these are features. Q data, search data, demographics, location, country, language, time of the day, season, all of that goes into our models. And then, what about models? The data, all of that, what kind of models we use. And here I'm just listing a few of the ones that we typically use. I'm not going to give many details, but you can think both logistic and linear regression, elastic nets, which is a very interesting generalized linear model using both L1 and L2 regularization, which is an extension of logistic or linear regression. SVD, I already mentioned, and RVMs, Markov chains, different clustering and other non-supervised approaches like LDA, association rules, GBDTs, and other tree-based methods like random forest. All of this comes into play using the data that I mentioned before. Okay, so is it about more data or better models? How am I doing on time? Okay, so I think this is an interesting question because it comes time and time again. And for example, during the Netflix prize, there was this post by Anand Rajaram from Stanford and now at Walmart saying more data usually beats better algorithms. And they were talking about the Netflix prize, and he was talking about how his students had taken some data from IMDb, content-based data, and had improved the results of collaborative filtering. Well, that was during the prize. Again, I don't know the date exactly, but is that really so? So later on, after the Netflix prize, we had a publication that said exactly the opposite. So recommending new movies, even if your ratings are more valuable than metadata. So what this publication was saying, it's like, forget about adding more metadata or more data related to the content. It's really not worth it. Just a few ratings, and they were showing how a few ratings in a well-tuned collaborative filtering environment was not really adding much to the precision of the collaborative filtering setting. So sometimes it's not really about more data. So another paper that people bring up, or another thing that people bring up when they're discussing about more data versus algorithms is Norvig saying that Google does not have better algorithms, it only has better data. And there's this publication, The Unreasonable Effectiveness of Data, that is related to this talk by Peter Norvig. There's also the famous paper by Banco and Brill in 2001, when they've basically shown for a language model that really very different models have similar performance, and they only really respond to how many millions of words they're being trained on in terms of what's the accuracy of the model. So the models really perform the same. So again, the question is, we don't need to worry so much about a model. It's just about adding more data. Is that really the case, right? So you have to remember that in both of these cases, they're talking about language models where you have low bias models and many, many features. And in those cases, it's reasonable to think that the more data that you add, the more the more examples you add to a high dimensional space, the more accuracy you're going to get. But that's not always the case. So just to give you a counter example, this is the current Netflix ranking system, and this is the number of training examples that we use, and this is the performance accuracy we get. So basically, as you can see, the model saturates very quickly, roughly, so this is 1 million examples, so roughly around 300,000 examples it saturates, and we don't need to use more than that. Because in dimensionality of the feature space, we have done some dimensionality reduction previously using non-supervised models, and we don't need to have that many training examples at that point. So again, sometimes it's not about more data. It's about how to be smart with the data that you have. I like to sort of unquote this article by Chris Anderson, where he was saying, the end of theory, the data deluge makes scientific method obsolete. And this cross that he was putting here, I put it on his article and said, okay, that's not really the case. What I'm saying is, data without sound approach is noise. So it's very good that we have more data, and the more data we have, the better, but that doesn't mean that our algorithms and a scientific method is obsolete. It's probably the other way around. You need to be even smarter to know what to do with that data. So, some conclusions. So the Netflix prize simplified the recommendation problem to predicting ratings, but as I mentioned, user ratings are only part of our many inputs, and they're only a small part of the problem, and now we are looking into many, many different sides of the different question. And so we have reformulated the recommendation problem, and the function to optimize is the probability that a user chooses something and chooses to watch it and likes it enough to actually come back to the service. And that's a complicated function to optimize, I can tell you that. And on the discussion about data or models, more data availability obviously enables better results. More data without a good approach, though, is noise. So we need to define optimization functions and metrics that enable fast experimentation. And something that we can do in industry, which is we're fortunate enough that we can do, is we can allow the user to be the final judge. So we basically have functions that we optimize offline, and all these machine learning models, we get our offline metrics, and we have a notion, an intuition of whether it's going to work or not. But at the end, we let the user, through A/B testing, answer the question whether model A is better than model B. And the cool thing, which we're trying to do, we're still not 100% there, then we want to correlate those offline metrics that I was saying before, like MRR, fraction of concordant pairs, NDCG, all of them. We're trying to build a predictive model that actually predicts the response we're going to get from the user. And that's the ultimate frontier of what we really want to be. We want to be able to predict how well a model will do once we launch it and we roll it out to the users by doing experiments offline in the lab. Okay, so that's the conclusion of my talk. Thank you very much.
Any questions?
So there was another more recent absolutist statement on the lines of we don't need theory, of the kind of A/B testing is good for everything. And you don't have to even bother to figure out whether something works for a user, just run A/B testing automatically, and it'll let it figure out what's the right way to present the data to the user. And since you mentioned various testing methodologies here, I'm curious if you would push back against that as well, based on your experience in Netflix.
I would. Is this recording going to be public? No, okay. So A/B testing is has the ultimate answer. The problem with A/B testing is it's very expensive and very slow. And I can give you an example. We had some linear model that was being used in production and have been kind of optimized. The weights have been optimized by doing A/B testing. What optimized means is that basically there have been a sample of this phase and oh, let's try with this weight, let's try with this other weight, let's run A/B test and let's decide what works better. Pretty recently, like 3 years ago, we actually did a machine learning model to learn those weights, and we said, forget about these models, these weights that we learned through A/B testing. Let's do an offline machine learning model, and let's A/B test it against the other one. So this model actually had the highest gain in all of Netflix history in terms of measure by user engagement. And you can say, of course, if you had infinite resources, infinite users, and infinite time to run A/B tests with every single possible combination of your parameters that you're going to roll out, then I would say, okay, maybe, yeah, go ahead and do it. But I don't know any company that has that, and I don't think it makes sense. What makes sense is to make a good offline optimization, sample the problem space, maybe come up with a reasonable, say, okay, the biggest issue with offline testing and the reason why it's not the ultimate answer is just because we're still lacking this perfect correlation between the offline metrics and what we see then with the users. And sometimes we even surprise ourselves and, oh, I had 2 models, this one got better, whatever, MRR, and now it turns out that users prefer this other one. So what did we do wrong? So we're trying to fine-tune this correlation. But if we have that, that would be the perfect thing. Like, we want to do things offline. A/B test is a good confirmation, but it's not reasonable to expect to optimize.
Muchas gracias. So I wanted to ask a couple of questions. So I'll start with, I think, the biggest one. I guess recommendation engines are a sort of big business now in general, and obviously Netflix has been way ahead of the game for a long time when it comes to sort of consumer-facing work. Is the fact that you're not using sort of third-party recommendation engines mostly a statement about how unbelievably important domain knowledge is? That, obviously you've got your own internal group to be able to do this, but if I now think about Netflix maybe pushing out the recommendation engines you've built, is the idea essentially that there is no sort of one way to do this right, not just in terms of the algorithm, but the whole framework for how you do the testing?
Yeah. Well, that's part of the reason, but I wouldn't say it's the main reason. I think the main reason is because we think that recommendations, personalization is so core to the business that we need to own it. Basically, Eric Smith from Google said a few months ago, he said something like, Netflix wouldn't exist today without the recommendation algorithm. I don't know, I wouldn't go so far, but the truth is that 75% of what people watch from the personalization and the recommendation. We have a limited catalog, and we have to really be good on presenting each user whatever what the user likes in a particular context, a particular time. So this is kind of like, it's like Google's secret sauce for the algorithm. It's not about saying, oh, we use page rank and everybody can use it, right? There's something else, and yeah, there is some domain knowledge, but it's mostly about, it's really like the core of our business is the recommendation side. So that's the reason why we don't want to either outsource it, base it on third-party solutions, or talk into many details about it.
the other thing I was just going to make a comment, which I'll give you for free, is something that I think can lift all of this very well, which is to use one piece of metadata, which I'm pretty sure you're not using now, which is the time when I'm looking at my recommendations, because at 11 p.m. I don't want to see Dora.
That's a very fair point, and I agree with you. You wouldn't be surprised of what people watch at 11 p.m. I think.
A quick question about one of the minor things you showed at the beginning in the matrix of rows by ranking, and you sort of said, oh, this is for dad, mom, child, Bob. How do you go about inferring the composition of the household?
We don't do an explicit inference of that, but we do an implicit one. So we don't really know whether you have two kids, daughter and son, or you're married or not. Yeah, I mean, we base, so many of our, solutions are based on some previous unsupervised learning methods that we use to cluster users or find taste clusters and then assign households to those. And that's kind of, we just know that you're roughly in an area, and that means that in your house it's probably people from that cluster.
Any more questions?
All right.
Let's thank you.
Thank you. That I come from a company, and I'm going to talk about one of our most valued assets, is my subtle way of saying that I'm not going to be giving too many technical details. Of course, I hope that I will make this presentation interesting to you for a different reason, because I'll be talking about the application of machine learning, data streaming processing in the context of customer-facing and industrial-scale applications such as Netflix. So I think there will be plenty of interesting things in the talk for you. Okay, so how many of you are familiar with the Netflix prize? Hands up.
All right, Xavier Amatriain?
That's pretty close, yeah.
Pretty close. He's a research engineer and manager at Netflix. Prior to this, he was a senior researcher at Telefonica, and also worked as the technical director of the Allosphere project at UC Santa Barbara.
Okay, yeah, so thank you very much. So yes, I'm a research and engineering manager at Netflix, and I'm going to be talking today about one of our most valued assets at Netflix, which is our personalization or recommendation. So say on 18,000 movies and around 500,000 users, and those ratings were from 1999 to 2005. And the contest, you had to pick 2.8 million ratings, which roughly was around 6 per user. With 10% better RMAC, that was a success metric we chose at that time. Okay, so in 2007, a year later, there was the Progress Prize. The famous Corbell team from AT&T at that time improved by 843, so that was getting close to the 10%, using a linear combination of 107 prediction algorithms. The top two algorithms are those 100. Okay, how many of you actually downloaded the data and played around with it, try to win the $1 million? Okay, that's pretty good. So for those of you that are not so familiar, let me remind you, this is a contest we put out at Netflix in 2006. What we were really interested at that time is how can we make better recommendations. But of course we had to find a proxy question, something that was measurable, something that we would put a number on, and that's the accuracy in predicted rating. So whoever was able to improve 10% the existing method would win $1 million. So here are some details on the contest. There were 100 million ratings. 107 were SVD, so a form of matrix factorization that probably most of you know, which had an RMAC on the prize data set of 0.89, and RBM restricted Boltzmann machines, which had an RMAC of 0.899, so pretty close. The linear blend had an RMAC of 0.88. So those are two of the 107. So what we did, because we got the source code for that, is we took that source code, we went through some of the limitations, for example, the fact that they were designed for 100 million ratings and we had roughly around 5 billion